So the windpipe of a typical whooping crane, if you've never seen a whooping crane, they look like this. So they're really large birds, and their windpipe can be up to 1.525 meters long, and they do make an interesting sound that I'm going to play for you real quick.
Hi, this is Lee.
So as you can hear there, they are making quite a racket, and they can make different frequencies with their voices just like we can while talking. Now, we are going to determine what the lowest frequency is that they can generate with their voices. And we're going to do that by looking at our givens. So we've got our length of our tube, which is the windpipe. The length is 1.525 meters. The temperature of the air is 37 degrees Celsius, which is going to impact our speed of sound. 37 degrees Celsius is pretty warm. And because this is an open, closed end on one side, open on the other to produce that sound, I've got my fundamental frequency drawn here. And so 1/4 of a wave is going to set up within the tube of length L. And so if we wanted to solve for the wavelength, we could rearrange that and say that the wavelength is equal to 4 times the length of the tube for a full wave, a full standing wave to form. Now, before we can find our fundamental frequency, we need to figure out how fast the air is traveling. And so to do that, we're going to use this relationship where the speed of sound at 0 degrees Celsius is 331 meters per second. And for every degree you change, the speed of sound will change by a factor of 0.6 times the temperature. And so I'm going to go ahead and plug in my 37 degrees. I'm going to do some algebra. And I'm going to have a velocity of sound at 353.2 meters per second. Remember, the warmer the temperature is, the faster sound travels. The colder it is, the slower sound travels through the air. Now that we have a way to determine the wavelength of the wave and the velocity of the wave, we are now ready to solve for that fundamental frequency. And so by putting our wave speed equation together with this relationship between lambda and length that we created from our diagram, I can then combine those together as a system and end up with my final equation that we derived in our notes. And our velocity will equal 4 times the length of the tube times the frequency we are looking for. So I'm going to go ahead and plug in my values. So I've got 353.2, that was the velocity I calculated. 4 times the length of the crane's neck times the frequency. And I'm going to isolate frequency by dividing by 4 and 1.525 on both sides. That cancels from the one side, and when I do the algebra, I'm going to have a fundamental frequency of 57.9 hertz. Now remember that fundamental frequency would be the lowest standing wave pattern that could form. That means that the lowest note that the windpipe of a typical whooping crane can support. So they cannot make sounds lower than 57.9 hertz. Now as they squawk higher, they could make multiples of that value if we were looking for the harmonics. Remember, the second harmonic would be double this value. So that is how we would find the fundamental frequency if we were given a temperature instead of the speed of sound initially. But it's very similar to our last example. The determining the speed of sound was the only real new step here. And the fact that instead of it being an open pipe, we had to determine our wavelength based on our boundary conditions, which was one end closed, one end open.